Hello students, welcome back. Before starting section 3, let's have a brief recap. Everything began from a non-empty set. Any non-empty set will do, and then from there we can form a group of bijections under the composition operation. In a special case, when the starting set is a finite set, we call such bijections permutations, and we can form the groups of permutations like this or like that. And then we call those symmetric groups. The permutations of symmetric groups can be written like this, and then we did some computation exercises. Also, we studied its particular subgroup, a dihedral group. But that was a bit of a side note. In general, for permutations of symmetric groups, we can consider orbits and cycles. The orbits are defined like this, and then we can define the lengths of orbits using the theory of finite cyclic groups. And then we can establish a decomposition by orbits using the theory of equivalence relations and equivalence partitions. Using the concept of orbits and decomposition by orbits, we can define cycles and decomposition by cycles. For example, here's a cycle, and this is not. And you can see that the latter is actually a product of two disjoint cycles, blue and red. And that can be generalized for arbitrary permutations actually. We completed up to that point. Now let's resume. First, let's take care of some lingos. A cycle of length 2 is called a transposition. That is, a 2 cycle is called a transposition. So everything remains the same, but we are switching I and j. And then the typical property of a transposition is times itself is the identity. So I goes to j, and then apply again. J comes back to I. Same goes for j, and everything of course remains the same. So transposition times itself is always the identity. Alright, I guess we are ready to the next theorem here, decomposition by transpositions. Every permutation of a finite of at least 2 elements finite set of. Sorry about that. Okay, I corrected. Every permutation of a finite set of at least 2 elements is a product of transpositions. If you have just one element, then there's only one type of permutation there. Just trivial group. So it's not interesting. So if our starting set has at least 2 elements, then we can consider some permutations there. And in that case, any permutation can be written as a product of transpositions. We are going to prove like this. Please recall that every permutation is a product of disjoint cycles. So it is enough to prove that any cycle can be written as a product of transpositions. Basically, it's this idea. If every cycle is a product of transpositions, gotta put some space in between, then you see any permutation can be written as a product of cycles, like blue times green times dot dot dot, brown like that. And then Each cycle is a product of transpositions, like this blue, and like this green bunch, and we have like this brown bunches like those. And then put everything together. What do we have? The starting permutation is a product of transpositions. So this is enough. That's what we are going to prove. So let's begin with a cycle. Let gamma be a cycle like this. Consequently, A0 is going to A1, A1 goes to A2, A2 goes to A3, and so on. And then AK minus 1 finally will go back to A0, and then the cycle repeats. In this case, we can rewrite gamma like this. And this gives you not only the proof, but also a computational formula. Remember, we are doing the composition, so the application is going from the right to left. So right first, and then next, and then the next like this. First, A0 goes to A1, and then A1 does not appear here anymore, so A0 goes to A1. You see? A0 goes to A1, and then A1 does not appear here anymore, so A0 goes to A1. Now, how about A1? A1 goes to A0 now, and then A0 goes to A2, and then A2 does not appear here anymore, so A1 goes to A2. Make sense? A1 here goes to A0, and then A0 goes to A2, and then A2 does not appear here anymore. Consequently, A1 goes to A2. Make sense? A0 goes to A1, and then no more A1. So A0 goes to A1, and A1 goes to A0, and A0 to A2, and then no more. So A1 goes to A2. Now, how about A2? A2 does not appear here. A2 goes to A0, and then A0 goes to A3. And then A3 does not appear here anymore. The next we have A4, A0, and then A5, A0, and so on and so forth. You see? So A4 will not appear here anymore. So A2 goes to A3. Now, if I start from A3, what happens? A3 does not appear here, so no choice. A3 goes to A0, and then A0 goes to A4. And then A4 does not appear here anymore, so A3 goes to A4. This just repeats. And then say AK minus 2 is not affected at all the way up here. And then AK minus 2 goes to A0, and then A0 goes to AK minus 1. Okay, we got to AK minus 1. And then if I start from AK minus 1, AK minus 1 does not appear at all. So it goes to A0, and that's it. And then we have a cycle. So starting from the right, apply those. And then as for this, it's not just a proof, it's a computational formula. A0, A1, A0, A2, A0, A3, A0, A4, A0, A5, and all the way up to A0, K minus 1 from right to left. Thanks to this, we ended up proving this. If gamma is a cycle, then gamma is a product of transpositions. We proved it now. And then please recall that any permutation is a product of disjoint cycles, and each cycle is a product of transpositions, and that they're all disjoint, so none of those affect one another. So what do we have? We have a product of transpositions. Now, is this product unique? That in general is not the case, but we do have existence. So here we go. decomposition by transpositions, we have it. You may have to remember this formula. This one here. So any cycle can be written as a product of transpositions through this scheme. This product may not be unique, but that's one way to do it. And then, of course, there are many cycles. Put all those together. Now, I said many times that the choices of those transpositions may not be unique, but the existence is there. Interestingly, however, how many transpositions are there? Well, that number itself is not unique, but whether it is even or odd, that part is unique. So whether a permutation requires even number of transpositions or odd number of transpositions, you can classify one with the other because that part is unique. How do we prove that? Well, that's something we are going to do in a separate video. It's going to be really hard, so I'm going to do it as an optional video. For now, let's just take it for granted. It is possible to classify all permutations in a symmetric group by even permutations and odd permutations. Even permutations require even number of transpositions, and odd permutations require odd number of transpositions. Moreover, the set of all even permutations form a subgroup. Well, even or odd, well, you can prove that they have the same number of elements. So the group of even permutations, this subgroup, has the half the size of the entire symmetric group. So the order of that is n factorial over 2. And this subgroup is called an alternating group. And it's pretty easy to see that E belongs to this AN because it requires 0 number of transpositions, or as a matter of fact, any transposition times itself is E. We saw that before, so we can say it's 2, or repeated you can get 4, and so on and so forth. And as for the odd permutations, it doesn't have identity, so that cannot form a subgroup. Alternating group will turn out to be important in abstract algebra 2 when we do field theory and Galois theory. But for now, it's a bit too difficult, so I'm not going to come back to alternating groups in abstract algebra 1. Just remember the name. And for that reason, I'm not going to overemphasize this proof. As for the proof that the alternating group or the set of even permutation is actually a subgroup or not? Good question. Shall I require that or not? I have to give some thought. I was thinking about requiring that, but I'm having a second thought right now. Well, I'll make up my mind by the time we begin the course so that I'll decide whether to write a homework problem associated to that or not. Anyway, we went through everything. Decomposition by transpositions, and then even and odd permutations and alternating groups, everything.